In this video, we're going to perform an FEA analysis on a conic structure configured in two different ways. In the first example, we'll have a pin-based pole with all of the perimeter posts restrained, but the top of the center pole allowed to move. And in the second model, we have a pole which projects above the bail ring and is restrained with cables down to the ground. So in the first example, we've got a 3D polyline that is the center post. The base of the center post is fixed with another 3D polyline, and each of the perimeter posts has two backstay cables and a 3D polyline anchoring each corner. The bail ring itself has been colored red. This can be any color, but I've selected red, which is color number 1 in the AutoCAD colors, as has the 3D polyline. So the two of them are both colored red. The posts and the backstay cables are simple lines in CAD. The blue lines are 3D polylines, which are fixed points for MPanel. Before we read the model in, we select the post and the bail ring together, and we set their status to link structure pair. So we set that, and you can see this was previously a link pair, so there's no change. We would then select the model. We want the program to automatically calculate initial tensions for cables, poles, and guys, so we've selected those. We want C lists, and it's a joined edge mesh as a single cone. Everything else is normal, and we select make model. I'll have it right over all of the materials and lists and select OK. Next, we're going to check the model. We'll specify a point to plot the restraints. Select plot. We'll then plot the cables and links in the same place. Now we can see all the cyan lines. The program is able to correctly estimate the initial tensions for all of these elements. Because we're going to be using asymmetric pressures on this structure, we're going to need M lists. In this simple example, we're going to use red and yellow, which is M list 1 and 2. To achieve this, we've drawn a simple polyline in red and another in yellow to cover the two portions of the skin that we want different pressures applied to. We go to the Lists tab, draw a list model. I'll take a copy to show the process of these two polylines. And then we select everything and read entities inside color polys. You can see all of the MList 1, which is red, and if we scroll down we'll see MList 2, which are the yellow areas. And to confirm this, we can draw a list model, and we can see here the areas in red are going to be MList 1 and areas in yellow are MList 2. The other areas will just be default values or 0. So next we're going to check the materials. We can see that the program has automatically identified the poles, and it's set the behavior as compressible, and all of the other cables it's assigned the default cable, which was 12 millimeters. We also have this pole link, and it's used the same EA value for the cables. We could change this if we wanted to, but realistically the link set, there are so many of them that this is not going to be a problem. pre-stress has been established by the material. Now MPanel+FEA always sets a conservative value here. I'm going to use a number of half of that, and we'll recalculate initial tensions based on that. Loads, at the moment we have no loads, so for wind up we'll use 1 kilonewton per square meter, and we'll do another one for load case 2 as a crosswind, where we want the wind coming from this direction. So mlist 1, the red zone, is going to be a negative pressure, so -1. The wind is pressing into the surface, and then we'll add another row, and for mlist 2, the yellow zone, we'll apply an uplift on the leeward side. So windward we've got a downward pressure, and leeward we've got an upward pressure. Go ahead and select load case 0, run the solver, and we get a very quick solid solution. So we know we've got a good, reasonable model. The same for load case 1 and load case 2. So we'll quickly review the plotted results for load case 0, 1, which is straight uplift, and load case 2, which, if you recall, we've got a downward pressure on the windward side and an upward pressure on the leeward side of the structure. Now, just for reference, we can see the compression in these posts, the reaction of 35 kilonewtons roughly, and the backstay cables are around 20 kilonewtons, and that should be consistent throughout the whole structure. We've also got a reaction of about 16 kilonewtons at the base of the center pole. And when we look at the membrane reserve factor, we can see we've got a little bit of extra stress at the top, which we expect. We've still got a reserve factor in excess of 5, but that probably suggests that we should look at some doublers at the top of the cone, double the thickness of the fabric to deal with the extra stress. Now, with load case 1, we've got a kilonewton of uplift, and we can see when we zoom in on the structure, the old is green, the new is black, and we can see the fabric's lifted up. We can also see the backstay cables in tension have allowed some movement forwards. It's on all sides. We can see the compression in the posts has increased substantially, and the tension in the backstay cables has also increased, but the compression in the center post has been reduced substantially as the whole structure is being lifted up. We can see the cable tensions have increased. There's the backstay cables. You can see a bit more stress in the fabric around the mid area, and we can see the reserve factor in the backstay cables with the cables that we used now down to a safety factor of 2. So again, we probably review the size of the cables and rerun the models with bigger cables for the backstays. Now in load case 2, we've got a windward load and a leeward load, so pressure down and pressure up, and here we can see and here we'll see the displaced shape. The center post has actually moved towards the windward side as a result of the downward pressure on the membrane. This side of the membrane has increased the stress in the fabric here, and that's actually pulled the top of the cone slightly to the left. If we look at the P-list reactions, we can see we've got -1 kilonewton in the X direction and 26 kilonewtons in the downward direction. We can also see, looking at the cable tensions that we've got asymmetry now in the backstay cables. So 33 here, here 36 and 30, so the structure's being pushed sideways, and here we can see 45 and 19. So a useful analysis. We can also see here we've now got no reserve factor left in the fabric at the top, so we've got very high stresses in the fabric here. Definitely looking to increase either the whole membrane to a stiffer fabric, or to include fabric doublers to allow for this additional stress. In the second configuration, the center post has been raised a meter higher than the bail ring, and we have, so this remains a 3D polyline as before. We also have now 4 lines which I've assigned the color green to, and an additional 3D polyline that restrains the base of these guy lines. So this represents a king pole with cable restraints to the top of the pole to the ground outside. Otherwise, the model is the same model we used in the previous example. When we plot the model restraints and the cables and guys from the Check Model tab, we see all of the cyan elements. The initial tensions are automatically calculated by the FEA software, and the magenta elements the software cannot calculate, so we need to manually establish initial tensions for these cables. As before, we're going to use M-lists and assign this quadrant of the membrane as M-list 1, which is the first color, and M-list 2 for the back half. So this will be our windward side, this will be our leeward side. We applied the same loads to the structure for locus 0, 1 and 2, and when we review the plotted results, we can now determine the tensions in these 4 ground cables that anchor the top of the post, and we can see now the top of the post is restrained, so it does not move like it did in the previous example, but we can see the asymmetry in the cable tensions. So this being on the windward side has a cable tension of 40 kilonewtons, and on the leeward side it's 52 kilonewtons. Here it's 46 kilonewtons. If you recall, the post was trying to move in the negative X direction when it was unrestrained. So now we've got more tension in this cable that is resisting that displacement. Thank you for watching. For more information, please contact support@MPanel.com.